You know, we're surrounded by billions of smart devices, but have you ever stopped to think about how they actually sense the world around them? I mean, from your phone knowing when to rotate its screen to your thermostat keeping the room just right, it all boils down to one thing: sensor interfacing. It's that invisible but absolutely crucial bridge between the real world and the digital one.
It really is the secret sauce behind pretty much every piece of modern tech we use. There are these tiny, amazing components that are constantly translating things like heat, light, and motion into data that a computer can actually understand. So let's dive in and pull back the curtain on how that incredible translation from signal to sense really happens.
So here's our game plan. We're going to start with the absolute basics. What even is a sensor? Then we'll get into the two main flavors of signals they speak, digital and analog. After that, we'll learn how to decode their language, check out some tools for a real project, and finally, we'll walk through how you can take an idea all the way to a finished design. Okay, let's start at the very beginning. To build anything, you've got to have a solid foundation. So what exactly is a sensor? Honestly, the best way to think of a sensor is as a translator. It's a device that takes some real-world physical thing, like temperature, light, pressure, you name it, and it converts it into an electrical signal. It turns it into a language that the brains of the operation, the microcontroller, can actually listen to, process, and then act on.
Right, so once a sensor has something to say, that signal has to go down one of two fundamental paths. It's either going to be digital or it's going to be analog. And understanding this fork in the road is, without a doubt, the most important first step to working with any sensor out there.
On one side, you've got digital sensors. They're super straightforward. They speak in black and white. It's either on or off, a 1 or a 0. It's direct, it's simple. On the other side, you have analog sensors. Think of these like a dimmer switch instead of a regular light switch. They give you a whole spectrum of information, all the shades of gray in between. They're way more detailed, but yeah, they do make the microcontroller work a little harder to understand them. So the whole deal with a digital sensor is that its world is binary. I mean, the simplest example ever is just a plain old switch. Is the door open? Yes or no. Is the button being pushed? Yes or no. It gives the direct, crystal clear answer that the microcontroller can understand in an instant. No translation needed.
But don't let that simplicity fool you. Digital sensing can get incredibly sophisticated. Check this thing out. It's called a gray code optodisk. What's happening here is a bunch of little optical sensors are reading this crazy pattern of light and dark stripes to figure out the exact rotational position of a shaft. And the coolest part? Because every single position has its own unique binary code, there's absolutely zero confusion about where it is. Even if you just turn the power on, it always knows.
Okay, let's shift gears over to the analog world. Unlike that simple switch, an analog sensor's output isn't just on or off. It's a variable signal that's proportional to whatever it's measuring. So a temperature sensor won't just tell you it's hot or it's cold. Oh no, it'll give you a very specific voltage that means it's 25 degrees or 25.1 or 25.2 and so on. It paints a much, much richer picture of the world. Now, every sensor you buy comes with what's called a data sheet. You can think of it as its instruction manual or its biography. And if you really want to use that sensor correctly, you have to learn to speak its unique language. And that language is all about a few key characteristics. And the absolute key, the Rosetta Stone for understanding this language, is a graph you'll find in pretty much every data sheet. It simply plots the sensor's electrical output against the physical thing it's measuring. The shape of that line tells you everything you need to know about its personality. So let's break this down. First up, we've got sensitivity. See that really steep line on the graph? That's a high sensitivity sensor. It means even a tiny, tiny change in what it's measuring causes a huge, easy-to-see change in its output. It basically screams when something changes. That's perfect for, say, an earthquake detector. Now, compare that to the flatter line. That's low sensitivity. It's more chill, which is totally fine for something like a room thermostat that doesn't need to freak out about every little draft. All right, next on the list is offset. You see how that graph line doesn't start right at the 0, corner? That little gap is the offset. It's kind of like the sensor gets a head start in a race. Even when it's measuring nothing, when the input is 0, the output is already some other value. It's no big deal. We just have to remember to subtract that head start in our code to get the real, true reading. And finally, let's talk about linearity. This is all about how closely that sensor's output follows a perfect, predictable straight line. For something like a medical thermometer, you need it to be perfectly linear, right? You want 37 degrees and 38 degrees to be measured with the exact same accuracy. But look at that curve on the graph. Some sensors are nonlinear.
Now, that's not a flaw. In fact, you often trade linearity for higher sensitivity. It just means our software has to be a little smarter to accurately translate that curve into a number we can trust.
Okay, that's enough theory. Let's make this stuff real. Let's pretend we're going to build a simple little weather station. What kind of sensors would we need in our toolbox? And, more importantly, what decisions would we need to make?
Well, for temperature, we've run into a classic trade-off right away. We could use a thermistor. It's super sensitive. It reacts really strongly to small temperature changes. But its output is nonlinear. It's that curvy line we talked about, which makes getting a precise number a bit tricky. It's great if you just want to know if something's overheating. Or we could go with an integrated sensor, like the famous LM35. It's perfectly linear, giving you a clean 10 millivolts for every single degree Celsius. For accurate, low-cost measurement, it's pretty much the go-to choice.
And what about humidity for our weather station? Well, we'd probably grab a capacitive sensor. It's a really neat design. They have this special material squished between two electrical plates, and this material just loves to absorb moisture from the air. The more water it soaks up, the more its electrical properties, its capacitance, change in a way we can measure. It's a super clever trick for putting a number on how humid it is.
So we've covered the what, we've covered the how. Let's wrap this all up into a simple, clear design process that you can use for pretty much any project you can dream up that involves a sensor.
And really, it boils down to these 4 logical steps. 1. Define your goal. What are you actually trying to build? 2. Select your sensors. Make that trade-off. Do you need crazy sensitivity or is pinpoint accuracy more important? 3. Analyze the characteristics. Crack open that datasheet and learn the sensor's language. Does it have an offset? Is it linear? And finally, step 4. Design the interface. This is where you plan the circuitry that will clean up, boost, or convert that signal so your microcontroller can make perfect sense of it.
And there you have it. We've journeyed all the way from a simple electrical signal to a complete system. We've seen how these amazing little devices translate the physical world into data, and we've learned the secret language we need to understand them. So really, the only question left is, now that you speak the language of sensors, what are you going to build?